Why can the sodium-potassium pump work backwards? In fact, can you help me understand how it even works forwards?
Hi, I'm Chris Masterjohn, and I have a PhD in nutritional sciences. I am not a medical doctor, and nothing contained in this episode may be construed as medical or nutritional advice of any kind, or a substitute therefore. This episode is meant purely as scientific education. If you wish to act on any ideas presented in this episode, please consult your physician first, and never take anything herein as a reason to contradict medical advice. With that said, enjoy the episode. Matt P. says, I'm having this issue understanding how a sodium-potassium pump can work in reverse. This article goes into it further detail, indicating how free energy can further synthesize ATP or pump sodium out. And this process is highly dependent on concentrations of ATP, ADP, and phosphate, as well as the gradients of sodium and potassium. I struggle to understand how the pump works normally, let alone in reverse. Can you advise on this? P.S. I dove into this a bit because of your last AMA regarding sodium potassium citrate supplementation as a way to reduce the need to go to the bathroom at night. Fell down the rabbit hole. I can explain it, but I think it would be easier to understand my explanation if I can pull up a diagram. And so let me pull up a diagram real quick and then share my screen. So I'm actually going to Google NCBI bookshelf molecular biology of the cell. And then I'm going to go to search this. You know what? Why don't I share my screen now so people can know how to search for molecular biology diagrams? Share screen. Okay. So all right, so what I did was I Googled NCBI bookshelf molecular biology of the cell. Now we're going to go to search this book and go to sodium potassium ATPase and hope it brings us to the part of the book pretty quickly. Could also do an image search, I think. I don't know if I found it. I don't think I found it. Let's all right, this came up because they're talking about. Okay, let me try a different search. So I'm going to go to NAK ATPase, see if that works. All right, here we go. So the section is the plasma membrane sodium potassium pump is an ATPase, and here's figure 1113. Let's try and make this real big. Okay, so first of all, I guess the first rule of this is that anything that is okay, so let's go back to potential energy. So if you're standing on top of a building and you have the potential to jump off, or to be a little bit less morbid about it, if you're standing on top of a diving board and you have the potential to jump off, you have potential energy by virtue of your position because you are high up. And because of the law of gravity, things that are high up tend to come down as long as there's nothing in its way. And so by being in the high position, since high things want to go down, then being in a high position is a form of energy, but it's potential energy because the diving board or the building is in the way of you moving. And as soon as you remove that out of the way, such as by supplying the activation energy involved in jumping, or if someone pushed you or whatever, then all of a sudden that potential energy is going to turn into kinetic energy until it's gone. So by the same, in an analogous manner, by the second law of thermodynamics, analogous to the law of gravity in the previous situation, everything wants to spread out randomly. And And that means that anything that's concentrated will want to spread out. And so an example of this would be if you take food coloring and you have a glass of water and you look at the food coloring, it's very concentrated. It wants to spread out, but the bottle is in the way. Now, if you just smashed the bottle and supplied the activation energy needed to overcome that resistance of the bottle, or if you emptied it up and you poured it all over your table, all over your countertop or whatever, food coloring would spread out to the extent it can by spilling all over the place until the surface tension keeps it there. But to use the analogy that I was going for before I went in that direction, if you just put a drop in water, what happens? Well, it spreads out. And if you just wait a few minutes, then if you take one drop of deep red food coloring and put it in a glass of water and wait a few minutes, especially if you stir it, it'll happen faster. But if you just wait a few minutes, you're going to get a very, very light pink kind of, whatever that dilutes down to, because those food coloring particles will have gone into the glass of water in one specific area. And by the second law of thermodynamics, everything wants to become disordered and to maximally mix and randomly spread. And so that's what it does. Okay, so the food coloring, by virtue of being concentrated, has potential energy in the same way that you had potential energy by virtue of your position when you were on top of a diving board that could be released into kinetic energy by you jumping off the diving board into the pool, or by the drop of food coloring spreading out to maximally spread through the glass. So both of those are potential energy that is energy in the form of position, energy possessed by virtue of position, by virtue of you being high up when everything wants to go down, or by virtue of the food coloring being concentrated when everything wants to spread out. So the best way to understand an electrochemical gradient is through understanding, I think the easiest way to think about it is to directly borrow from the food coloring analogy. So if you were to take sodium and, more accurately, if you're in your kitchen, to be taking sodium chloride, but ignore the chloride for now. And let's just pretend that's sodium by itself. And if you were to put a bunch of sodium in a glass of water, do the same thing as the food coloring. It would start to spread out and mix out. If you stirred it, it would happen faster, but eventually it would thoroughly mix with the glass of water anyway. As long as you didn't exceed the amount of the saturation point. So sodium, just like food coloring, wants to spread out. And especially in your body fluids, this is ionized already, so you don't have crystals that have to break down. It just always wants to spread out. So the second law of thermodynamics says everything that is high concentration wants to become a low concentration. Just like the law of gravity says everything that's high up wants to come down. Everything that's in high position wants to be low position. Low concentration means everything's spread out. High concentration means everything is not spread out. So if sodium is at a high concentration right here, it wants to spread out to places where there is no sodium, so it can achieve a maximally spread out, randomly mixed, low concentration everywhere. And so if you just put some sodium here and all this fluid can be occupied, it's going to flow over here. Now, that principle is called a chemical gradient. The reason they call it an electrochemical gradient here is because sodium is also positively charged. And so you not only have a concentration of a chemical, sodium, right here, but you also have a concentration of positive charge right here. And so because the positive charge wants to mix with negative charges, then if you have more positive than over here, and you have relatively, negative charges over here, the positive charge will want to mix with the negative charges, in addition to the fact that the sodium that's concentrated one place wants to maximally spread out. And so because sodium is both a chemical and an positive electrical charge, we call it an electrochemical gradient because it's trying to satisfy both conditions of spreading out the positive charge and spreading out the sodium. The potassium is the same exact thing. So if you took some potassium, if you had potassium chloride or potassium citrate or potassium bicarbonate in your kitchen, do the same thing in water. Ignore the citrate, bicarbonate, or chloride. Just pretend it's potassium. It's going to spread out in this exact same way for the exact same reasons. Okay. So because of that, if you have a concentration of sodium on one side of the membrane, that is a form of energy because it's potential energy by virtue of position that will want to transfer into kinetic energy in the movement of those sodium ions to everywhere else that they're not. Now, to take advantage of this, you stick a membrane in the middle. This is analogous to water, using water power with a dam, right? So water that is high up wants to go down because of the law of gravity. And so to get from high to low, water releases kinetic energy. But if you want to use that kinetic energy, you want to be able to control it. So what you do is you put a dam there. That way the water stops at the dam, and only when you say so does the water release its potential energy in kinetic energy, trying to go from a position high up to a position down low, obeying the law of gravity. And if you can funnel the water through the hydropower plant, you will take the kinetic energy of the water and you will use it to make electricity. That is exactly analogous to how this membrane functions. This membrane says, sodium, you ain't going anywhere. Potassium, you're going to stay put until I say so. And the thing that says so is the hydropower plant, which is the ATPase. You know, incidentally, ATPase means it hydrolyzes ATP. When it's operating backwards, it's not doing that. So, but anyway, and so to think of this as functioning to make ATP, well, let's cover how it normally functions. Actually, you know what? I'm going to bring up just to sort of complete this analogy. I want to go to let's get a diagram of let's see, ATP synthase. So this is going to be okay. So this is let's complete the analogy to the hydropower plant with this. So what's happening here is that you're in the respiratory chain. You know what? Let's get the all right, just for the sake of time. Over here, there's a bunch of hydrogen ion pumps. And so you're taking energy from food molecules and you're pumping hydrogen ions to this side of the membrane. The membrane is your dam. The hydrogen ions are like the water in a hydropower plant. And ATP synthase is like the turbine in a water power plant, where this dam, the membrane, says hydrogen ions you can only get across the membrane, which we know you want to do because of the second law of thermodynamics that says any chemical will want to maximally spread out and mix around, and any positive charge will want to do the same. So you have an electrochemical gradient with hydrogen ions. This hydrogen ions, because they're concentrated on one side of the membrane, they want to get over here, just like high water wants to go to low water. And this membrane is like the dam, and ATP synthase is like the is like the turbine, the hydropower plant. And this is shown in cartoon form, so you don't see it, but this literally it's a turbine that is made of protein. And as hydrogen ions are let through, the kinetic energy that they release by moving to a position of high concentration, from a position of high concentration to a position of low concentration, that kinetic energy spins the turbine, and the kinetic energy spinning of this turbine spinning is then transferred to ADP and phosphate to supply the chemical bond energy that is needed to glue together the phosphate to ADP. And so that is very analogous to the hydropower plant having the water move through the dam, spin the turbine, and create electric power. Then that can be stored in some way that can be released when you plug something into your wall. But in this case, the stored form of energy is in the chemical bonds of ATP. Okay, so knowing that, now let's go back to the sodium potassium pump. So usually what's happening is if you want sodium to be at a place of high concentration instead of evenly mixed, you have to reverse the process of spreading and thereby violate the second law of thermodynamics. You're not actually violating the law of thermodynamics, but you are effectively reversing the process that it generally imposes on the universe by an investment of energy. And so, just like it takes energy to climb up the ladder to get on top of the diving board or the building, or just like it takes energy for a production plant to put food coloring into that little bottle, so it takes energy to put sodium all on one side of the membrane if where sodium wants to be is spread out. Similarly, it takes energy to put potassium all on the other side of the membrane if where potassium wants to be is spread out. So you take the chemical bond energy in ATP, you break off the phosphate bond and release the chemical bond energy stored in that terminal phosphate, the last phosphate of ATP, and you take that chemical energy and you use it to supply the pump with the kinetic energy that it needs to shuttle or move sodium to one side of the membrane and potassium to the other side of the membrane. So remember, to concentrate something requires investment of energy. To relieve a concentration of something releases energy. So if this is going to operate in reverse, then sodium is just like ATP has potential energy in the form of a chemical bond, which is also by virtue of position, by virtue of these two atoms being, in a certain proximity to each other. So sodium has potential energy by being concentrated. And if it's going to flow through to the opposite side and potassium is going to do the same thing, then you're supplying the kinetic energy needed to store ATP. So asking how can it operate in reverse is saying, well, how could you power a water pump? If you let's say you have an electric pump because your basement got flooded and you're going to pump the water out. What are you doing? Well, you're doing the reverse of basically what a hydropower dam does, where it takes naturally high water by virtue of flowing down a mountain, and it stores the energy with a dam, and then when it says so, it releases the water to take advantage of the kinetic energy to make the energy that to turn the turbine, make kinetic energy that will then be stored in the form of electricity. But if you take a pump to pump out the water from your basement, you're plugging into the wall where you have stored electric energy, and then you're using that to generate kinetic energy to move the water away from where it's spread all over the place to concentrate it into some other place. So this is exactly the same thing. It's just instead of human choice being the thing that dictates it, it's that anything on anything that is high concentration wants to go to low concentration, and for reasons that are harder to understand. Well, the easy way to understand it is just that if the state of energy in the cell is no, let me put it this way. Think of the concentrations of ATP and ADP. There's a very high concentration of ADP, which means you're about to die. If it was really high, then this favors going in the opposite direction to synthesize ATP, providing you have the energy investment that you need to do so. Whereas if you have a lot of ATP, this favors the ATP going in the other direction and releasing that energy. And that's because the concentration, and I need another diagram if you want me to go into this in detail, but the concentration of any chemical reactant dictates the speed of a reaction. And most reactions can occur in a bidirectional manner so long as the energy available to make it go one way or the other is available to the reaction. So if you have a high concentration of ADP, that naturally produces a state where this ADP, if the energy is available, does want to go in the opposite direction. But that energy being available would mean that this pump has been very effective, or some other means has been very effective in making the sodium very highly concentrated out here. So we have very high concentrations of sodium on the outside of the membrane and very high concentrations of potassium on the inside of the membrane, where essentially the pump doesn't need to do the work of putting them there because they're already there. And you also have very high concentrations of ADP and low concentrations of ATP. Then instead of using energy of ATP to pump those to each side of the membrane, you will use the energy in the concentration gradient to drive the synthesis of ATP, just like the way you usually do in the electron transport chain when you're using the energy stored in the hydrogen ion gradient to synthesize ATP. Okay, so I know that was a lot of where's my, let's see, stop share. So I know that was a lot. And so if you have any follow-up questions, let me know. Okay, so Matt follows up, is there an intracellular potassium cap, or is that cap predicated on available energy to pump potassium in and sodium out? It went into depth on potassium leak channels, and so it made me think, if I don't have energy to move potassium in, would potassium supplementation be pointless? I don't know if that's even a proper question. Okay, so there's no cap on potassium, but if you keep pumping potassium in, you are exhausting, you are sort of creating, remember, the second law of thermodynamics is everything wants to spread out. And the more concentrated something is, the more it really, really wants to spread out. So if you keep pumping potassium in, eventually there will be so little potassium on one side and so much potassium on the other side that it requires more and more energy to invest to pump it there. Meanwhile, if there's any way to escape it, really wants to, because you made it really concentrated. You're investing energy in counteracting the second law of thermodynamics, and the second law of thermodynamics is getting pissed, and it's going to fight back. There's a way to think about that. Now, if you don't have enough energy to pump the potassium in, yes, you're correct. The potassium is not going to get in there. But if you don't have any energy, you already died a while ago. So you always have some energy. But yeah, I mean, I think energy deficits are going to be a major reason for electrolytes not being properly balanced across membranes. All right. Matt follows up and says, thank you. You're welcome, Matt. Glad I could answer your question.
This episode was part of a Q&A for members of the CMJ Masterpass, where I hold monthly private Zoom Q&As for my members. The Masterpass also serves as a buyer's club with exclusive and massive discounts on your favorite premium foods and health products, including pasture-raised and wild meat and seafood, supplements, sleep accessories, water filters, phototherapy devices, and much more. If you'd like to participate in these Q&As, you can join the Masterpass at chrismasterjohnphd.com/masterpass and use the code Q&A, spelled Q-A-N-D-A, Q&A, for 10% lifetime discount. I am currently working full-time on finishing my first book, Vitamins and Minerals 101, How to Get the Nutrients You Need on Any Diet. I will let you know when I have a release date. In the meantime, you can pre-order the book at chrismasterjohnphd.com/book. Testing Nutritional Status, the Ultimate Cheat Sheet, has been newly released as version 1.3. This is my comprehensive system for managing nutritional status with lab tests, dietary analysis, and comprehensive intake of your signs and symptoms. The new version has a comprehensive guide to interpreting the Genova methylation panel. You can pick up your copy at chrismasterjohnphd.com/cheat sheet. In my consulting, I am neither a medical practitioner nor a coach. I serve as your data analyst and your strategist. I teach you scientific principles of health and wellness, help you analyze your data, and help brainstorm actionable strategies. You can sign up for a consultation at chrismasterjohnphd.com/consultations. Please consider supporting my work at no extra cost to you by visiting my support page and making a purchase with one of my affiliate links. Some of my most popular affiliates are also listed in the description of this video with links that will give me credit for your purchase. I will try to respond to comments when I can, but my presence will be intermittent while I'm finishing my book. I hope you enjoyed this, and I will see you in the next episode.